talk earlier, and what we're going to talk about is mostly around the use cases and what this means in crypto. So from a high level, Inco is a EVM that has fully homomorphic encryption added to the EVM, essentially. So the problem we're trying to solve here is around confidentiality. There has been two historical types of solutions. One is to use secure enclaves, like Intel SGX. The other one is to use ZK. So generally, the secure enclaves do work. However, they're a little bit more centralized because they are prone to side channel attacks. And this has also happened in the past with Secret Network, where the private key got leaked. ZK here does provide privacy. However, it's limited. It's very limited in certain use cases that we will cover next. Actually, maybe just talk a little bit more. The reason why it's limited is everything you do with ZK happens off-chain, from the data you're trying to prove to the circuits to the prover. So this means that you need a off-chain infra to coordinate certain state transitions, and this is where FHE here really differentiates itself. So we just went through a pretty comprehensive FHE overview, so I'm not going to spend too much time here. But for people who are non-technical, the easiest way to think about FHE is that imagine you have a cat picture, you encrypt the cat picture, you can still modify the RGB values of that cat picture using FHE by manipulating the RGB values using additions, multiplications, divisions. And when you decrypt, you have this automatic filter applied to this. So it almost works like magic. From a high level, the difference between FHE and ZK here is really the idea of composability. So if everything happens off-chain with ZK, the challenge here is one is the trustlessness, right? So you have to kind of trust that people have what they're claiming to have, let's say for a poker game. But more importantly, it's around composability. So the challenge with composability is that all the hidden states are stored off-chain, so you need a centralized prover or coordinator to basically do the state transition on your behalf, so it's no longer permissionless. The second problem is ZK is not a cryptography that enables state transition over encrypted data. It has to be over plain text. So at some point, if you, let's say, build a game with hidden information, during that state transition, there could be information leakage from this centralized system or service. FHE, on the other hand, is meant for you to do computation on top of encrypted data. So in the context of crypto, if that encrypted state is on-chain, it can directly transition fully on-chain without having to decrypt in the process. And so this is where you have composability. So if you build a game or something like private voting, you can directly increment people's scores or tally directly using FHE. So if you think about this, when people come to Web3 today, they will quickly realize that they can only build use cases that make sense on a transparent database. But this is not how Web2 works. Like, what if you want to build a poker game? Ideally, you want to be able to store information on-chain in a confidential manner. And we all love blockchains because they are public ledgers that we can all trust. But it doesn't mean that all the states needs to be public, because then you'll be very limited in the types of use cases you can build. So we think we can unlock quite a bit of new novel use cases in this space. So what does this look like? It's an EVM that has been augmented to support additional types and operations. So in the context of EVM here, you have this encrypted types called EUINT, which represents a hidden integer. And then if you do an ERC20 transfer, you can add an encrypted amount to an encrypted balance. And this is all done using FHE, meaning that your balance, but also the amount being transferred is also hidden from the outside world. We can also do on-chain randomness that can be quite useful for games and such. But what really differentiates FHE in the context of confidentiality is really the idea that you don't need any secure enclaves that's centralized. You don't have to write any complex circuits, or you don't need any centralized off-chain coordination. This is all happening on-chain, and the coordination layer is the protocol itself. So the way this works on a high level is you have an EVM with a FHE Rust library at a precompile level. So this means that whenever you need to execute FHE operations, there is a Rust library running TFHE in the backend to do computation. There is a global FHE key here. You can think of it as a public-private key. But the private key doesn't exist because this is generated through DKG at Genesis. So none of the validators have the entire private key. the idea is that if you want to store an encrypted data, you will use this public key to encrypt your data on the front end, on the client side, and then store it on-chain. And the reason why there is composability is because we're all using the same public key to encrypt the data, and then you can do computation. And when you need to decrypt, each validators will do a partial message signing. You aggregate enough of them to recreate the plain text based on the threshold, basically. So now moving to use cases. So there could be a lot of use cases across different verticals. So let's first talk about gaming. Because we have on-chain randomness, we can easily enable fully on-chain casino games. So roulette, you can also do poker games because the randomness by default is actually hidden. And so this is not even possible with chaining DRF because that randomness is actually in plain text. For us, if you want to generate a hidden roll, a hidden card, this is going to be very easy to do. We can do all sorts of hidden information games. So if you think about it today, there's the reason why crypto games are not as fun as they could be is because they're built on transparent databases. If all the player stats, hidden game states are known, there's no challenge, right? Why should I attack you if I know you're going to beat me, right? So for us, just adding a layer of confidentiality, let's say on the player stats, already creates more mystery and more fun. We can fundamentally enable novel types of games that has to do with bluffing. You can sabotage people, you can spy on people, you can conceal resources, you can form secret alliances. DeFi, we can do fully on-chain, dark pools, spy AMMs, blind auctions. The idea is that there will be novel primitives that has to do with confidentiality. And with the randomness, I think an interesting idea is also you can gamify DeFi. So there's a project called Let's Pull Together where one person gets the yield from everybody as a lottery. So you can do this fully on-chain. You can also gamify other types of yield in DeFi down the line. On the enterprise side, payroll is quite interesting because in the example I showed earlier, ERC20 transfer, only the amount is being hidden. So this means that it's still fully auditable on-chain. If I look at Etherscan, you can see that people have transferred money to each other. It's only the amount that's being hidden. A little bit different from the ZK approach where everything happens off-chain and you're hiding from and to. So this is where oftentimes you could run into money laundering problems or terrorism funding. So this is fundamentally a novel type of approach. We can do private cap tables. We can also do security tokens on-chain where you can decide which layer information you want to hide. Maybe it's just the amounts. Maybe if you want to hide the ownership, you could also do it. But this is where, like I said, there could be compliance issues if you do that. We can do real-time predictions. So imagine we all predict the price of Bitcoin. We can still calculate the average price prediction without having to decrypt. So this kind of changes the dynamics, right? People can't copy each other's answers. If you see a whale making a prediction, you're not going to copy their answers, right? We can do private voting. So private voting is also a multiplayer use case that requires composability. When you do it off-chain with ZK, you will need some kind of centralized coordinator at some point to do the tally over plaintext, which could leak information. So this is generally a lot easier to build on FHVM. And also confidential DID that we'll cover in a bit. So yeah, so this is a simple game that we built last month at ETH Global NYC. Here, who has ever played Mafia game before? Does everyone know what Mafia game is? Okay, so in this game, basically you play with 5 or 6 friends. There are hidden roles assigned to everyone. You could be the killer, a doctor, or a detective. So the idea here is it's a game of bluffing, and everyone has to figure out who the killer is. And here, the role is fully generated on-chain, your hidden role, directly on-chain. It's also hidden as an EUINT 8 type. And all the game states are also stored on-chain. So if I attack someone or save someone, the information is protected so that you're not leaking what your role is. When you try to build this in ZK, it's also the same problem, right? So potential information leakage. The prover will see everyone's hidden state at some point because to do state transition off-chain, it has to be over plaintext. And we can also do all sorts of randomness games, slot machines very easily. We can also do poker games, like I mentioned earlier. We have that native confidentiality, which enables you to do card games. And yeah, so DID is a quite interesting use case because historically the DIDs that we have are soulbound tokens. So you KYC with someone, they sign into you. It will say, hey, are you over 18? Are you in Europe? But this is quite inconvenient because everything is public. Like, what if you want to hide some information? So with FHE, what's interesting is not only you can do operations, you can also do comparisons. So for example, if I store your credit score fully on chain in an encrypted manner, I can expose a function that says your credit score over 700 without leaking the original information. So this means that you could have a system which is more of a dynamic DID and programmable DID. For example, you could have various information stored on chain and expose different endpoints, like are you over 18, are you in Europe? And it's very similar to a Web2 experience like Google Auth. When you connect to an application, you can say, I want you to access my calendar, but not my Google Drive or my contacts. And then you can also say, maybe for a casino dApp, I just want you to know I'm over 18 and nothing else. So the way this will look like is very easy. You just do a FHE comparison. You do a tFHE.greater than. You compare the credit score with the 700. And then you decrypt the answer, whether it's true or false. And this is very easily achievable. Now, one thing, this is a little bit more technical. The idea is, how do you build application logic on-chain in a confidential manner without leaking information? So for people who are developers, the idea is if you store confidential information on-chain and you have if-else statements to do different logics, that could potentially leak information because depending on the path of execution, you could also just basically say, this is your hidden information, right? So one way to do this is something called CMUX. It's a multiplexer. So it's essentially like a ternary. So a ternary, as an engineer, it's basically if the condition is true, you return this value. If it's false, you return the other value. So the first thing, so this is a private voting contract. It's only 5 lines of code. What you do is you pass in a encrypted choice that could be 0 or 1. And the first thing you do is you compare whether the choice is equal to 1. And what this returns is an eBool, which is an encrypted Boolean. The next thing you do is you pass in this choice into this multiplexer function that will return the encrypted vote count if it's true, and 0 if it's false. But 0 is also encrypted. So what you end up getting here for in favor count to cast, it's either 0 or the encrypted vote count, but it's encrypted, so you don't know from an outside perspective. For against count to cast, you do the exact opposite. You will return 0 if it's true, and then encrypted vote count if it's false. So what you end up is like one of these two values will be the actual vote count. The other one will be 0. You add both of them to their respective hidden tally. And so this is how you're able to do a form of if-else statements without linking information. To get started, it's super simple. You essentially import this tFHE.sol library at the top. If you want to build something on Inco, you have to use 0.8.19 for now. We will basically upgrade our EVM down the line to support post-Shanghai, basically. And there is a JavaScript library on the client side that enables you to generate the ciphertext. And Nitenshu earlier covered what a ciphertext is the way you hide data. From a high level, there's data, some noise, and some noise padding. So let's say I want to pass in a value 100 in an encrypted manner on chain. So how do I do this? I will use this FHE library to generate this ciphertext and then pass it in as a parameter directly as a call data. And then here you can do tFHE as EUNS8 to convert the ciphertext into a on-chain encrypted value, basically. And so right now we support EUNS8, 1632. We will support 64, 128, 256 down the line. So it is doable. It's just very slow to compute for the larger integers. And down the line, there will be ways to scale FHE using specialized hardwares and things like that. So yeah, what we can support here is actually quite wide because we're using tFHE, so we can multiply, divide, add. You can do bitwise operations. You can also do all sorts of comparisons that are quite useful for a general purpose EVM. The idea here, yeah, if you want to build a private AMM, private DeFi, or any games, it's quite helpful to basically be able to do a broader range of operations. And there are two types of decryptions. One is tFHE.decrypt. Essentially, this will decrypt for the entire network. So this, whatever plaintext that gets revealed, will be revealed to the entire network. You only want to use this if you're comfortable with this idea that everyone can see this. So for example, for a poker game, at the end of the round, you want to reveal everyone's hands, right? So you probably use this function. There is a view function that's meant for, let's say, you just want to see your own balance without revealing to the entire world. So this is something called re-encrypt. The idea is you would generate a temporary private key and public key on the browser side. You hide the private key temporarily in your browser. You pass in this public key where the validators will basically re-encrypt the signed messages using this public key. And by the time you return to your browser, you will basically be able to decrypt and aggregate all the partial signatures we create in plain text. So this is, for example, in the context of ERC20, you can just do a view function to view your own balance. Or in the Mafia game, maybe you just want to view your own secret role. You also use this function. So yeah, we're fully compatible with most of the Ethereum toolsets. MetaMask, Hard Hat Remix, very easy to onboard. This is because FHE has been added at the precompile level, meaning that the compiler has not been modified. We're not adding any new opcodes. We're not changing the compilers. That's why this is still fully compatible. We did kick off a hackathon 2 days ago. The winners will be presenting later today, after 3:30 p.m. So yeah, quite excited about some of the projects that got submitted. If you're around, yeah, feel free to check it out. And then we do have a list of FHE VM ideas that we have provided. I think this is generally a pretty greenfield industry. I think we've been very conditioned to think that crypto applications have to be transparent. So I think we can open up for new types of applications down the line that could be more fun or just more practical down the line. So this is our information if you want to link with us. If you want to collaborate with us, we have Suraj over here in charge of collaborations. Yeah, we also have t-shirts here. Feel free to grab some. Yeah. Yes, this is last slide. I can go over questions. Oh, yeah.
Any question, guys?
So you mentioned that you have one private key, essentially, or like one secret key that encodes everything. Yeah. So does that mean bootstrapping doesn't work then?
Sorry?
Does bootstrapping still work?
Yeah, bootstrapping works. The private key here is mostly meant to encrypt and decrypt. The FHE bootstrapping happens, regardless. Yeah.
In your previous slide where you were showing the architecture where there was a private key between all the networks and it was a global private key, right? Yeah. So like how is this like FHE, global FHE is generated, and does a validator, if a validator holds this key, can he like the validator go wrong and decrypt the data and read everything?
Yep, so the way you guarantee some level of security, at least on the privacy data, is because this global FHE key is generated at genesis through DKG. So non-validators, each validator will contribute some entropy together to create this random FHE key. And so this is where a single validator would never be able to cheat and decrypt all your states, right? There needs to be a threshold. So it could be 3 out of 5 or 7 out of 10. The idea is like everyone will do a partial work of manual signing, and you need to aggregate enough of a threshold. Yeah.
Okay, so it will be just reconstructed for the signing part, and then no one validator will ever hold the whole private key, right?
No.
Okay.
To encrypt, it's permissionless. You do it on the browser's end. You just use a public key. To decrypt, there needs to be work from the network to decrypt. Yes.
So, for example, in the credit score example, if let's say I'm storing a credit score on chain after making it, encrypting it to FHE, I'm also able to compare any value against the value, right? And I know credit scores only go up to like 1,000 or whatever they go up to. So I could technically just brute force it if I run through. So that is a possibility.
So yeah, the idea is like each of these functions could be some kind of like plugin. So almost like account abstraction with a plugin marketplace. So maybe you as an end user, you just want to enable people to see if you're above 700 or below 900, right? So you're not giving people the choice to pass in what score they want to compare against. You as an end user, you define, hey, I just want you to know these two specific insights. So this is how you can prevent the issue that you mentioned, the brute force issue.
But the TFHE encrypted value is available to me.
Correct.
And I can encrypt any number through TFHE without sending it on chain.
Yes.
And then I can perform the operation off chain, the comparison, or does it have to be on chain?
It has to be on chain. So this is where the decrypt function is a function on chain that you have to call in the smart contract. And then this will instruct the validators to do the work to decrypt.
Okay. Okay, understood. Yeah.
One last question. Just let's say if I have a contract which holds balance or something like that, and then I have method to encrypt it and then store it on EVM, right? And then so someone upgrades the contract and update a read method where he's like just decoding the balance and returning it back. So doesn't it like everyone will be able to decrypt it and read the data?
So this is why you have two different decryption functions. This one will reveal the plain text to the entire network. It will be more like permanent. This one is more of a view function where the way you hide data is you pass in another public key so that the validators will encrypt all the partial signed messages with this public key, return to your browser, then you decrypt all these messages to recreate the plain text. Right, so this is what you want to use in the context of ERC20 transfers.
So this is not a read function then?
This is read function. This is, it could also be a read function. It could also be a permanent state change function, yeah.
Can I ask one question on behalf of audience?
Go ahead.
Yeah. So let's say like I basically deployed an ERC20 contract on top of Enco network. And what I actually did is like, let's say currently I'm the owner of that particular ERC contract. So firstly, I made the transaction of one ERC20 token, then made the transaction of 2 ERC20 token, then 3, then 4, then 5. So basically, I have the ciphertext matching corresponding to the plain text matching. I actually knows like what's the ciphertext look like for all the numbers from like let's say 1 to 10. And basically, kind of like I exposes that particular mapping. That 1 to 10 number, basically, these are the encrypted formats available on chain of those numbers.
So you wouldn't be able to do this because there is some randomness, right, in that ciphertext. So if you encrypt the number 10 times, it will all look different. So you would probably never be able to map out everything here.
Yeah, I just wanted to touch on that one.
Yeah.
Any more questions? Cool. I think it's over.
Yeah. Well, thank you, everyone.
Big round of applause for Remi.